Well, let's start. As I promised, I will show you how to use that little shifting program. That's coming. That was developed as the grandfather of the whole EMD. It actually was developed around the time of 1995 to 1997. A postdoc that that worked with me developed this program. This program, let me start showing this. This program has this little logo. I believe most of you has already downloaded, right? It's an executable. The program was written originally. The program was written in MATLAB, and then when the postdoctor joined me, and he suggested the MATLAB is no good, it's too slow, we have to use something else. So he decided to write a C program language for the shifting, so it would be faster. But this gentleman is really extremely smart. He has never written any program in C language, but he thinks that it should be in C language. So he started work on C language. For 2 months, I didn't heard anything or didn't get any result. So finally I asked him, so what happened? He said that the program should work, but somehow the address is a little bit wrong. It turns out somehow the read or input and output the program is a certain format requirement for the C language. He didn't know how to do that. So I said, do you have a menu? He said, no. I said, well, why don't you have a menu? He said, menu is too expensive. I said, how much? He said, about $200. I said, listen, your salary is maybe 20 times more than that. Let's go to the bookstore and get a menu. So I went to the bookstore, bought a menu, and gave it to him. The next day, the program worked. That's basically this program. And we have been using this until NASA decided to write a different program. And but the NASA program, I cannot give it to you because NASA has patent control. The program, when finally the NASA tried to write NASA program, I give this program to NASA. And the computer scientist spent 2 weeks trying to understand what the program is. But he failed because he said that the program is written in so unconventional way that he cannot track all the logics. So he said, might as well to rewrite the whole thing from scratch. So the NASA program is totally independent of this one. This one works, but apparently no one really understands the logic step behind it. So if you click this, a window will appear. And this window is what we want. You see here is a readme first. I have transferred this program from one computer to another. Somehow the readme file failed to link to this. But I did give you everyone a Word file, right? README Word file. I hope you have already got it. And here is another one. It's the NASA patent. You can see that the patent pending. This was written in 1995 and 1997. Our patent has not been approved, but right now it's already approved. To run the program, here is another box. This box is to say check intermittency. Let's put that aside for the time being. Let's say we want to run the program. Once you click that run the program, and what will happen is that it will ask you, where's your data? Okay, so you have input data. My input data in this case is in D and LOD 62. That's my data. And the output, I also want to put the output in certain place, and the output I will call C62. That's whatever file we want. Okay. The input data has to be has to be in ASCII for this program to run, and can only accommodate one column, no two-column data. If you have two-column data, the computer don't know what to do. So if you have data time and the data, take the time away, put the data in first. Okay? So once you get that, you say, okay. So what happened is that immediately it took the data. It will ask you whether this is the data. This is the data, and this data total length is 14,232 points. Okay? So it count the points, it says, is this your data? And if this is okay, you just click OK. Then the next box is important. The spline 1, spline 2, spline 3, spline 4. Don't use the other one. Like the 4 sometimes does not converge. That's when we try fancier splines. Okay? So spline 3 is the cubic spline. And here is the maximum shifting time. At the beginning, as I said, we are not sure whether using different spline will converge or not. So we put a upper bound here. Upper bound here, default is 10. That's a little bit too not enough. So I usually put it in 100. And minimum shift time. That means at least you have to shift once. So that's the minimum shift time. This is no bad point. My postdoc is from mainland China. He started in Paris. So when he wrote, he said, well, this check is to check, see whether this is basically the stoppage criteria. Okay? But instead of say stoppage criteria, he says, let's check whether there's any point that we don't want. So he directly translated that to no bad point. No bad points 3 does not mean we tolerate the 3 bad points. 3 means we count consecutively the shifting. If we shifted once, we have extrema equal to 0 crossing. Then we have to say we shift another time, extrema equal to 0 crossing, and equal to the same time, M1. And if the third time is also M1. So that's consecutive 3 times. It works. Okay? Then we stop. If you change that to 4, that means you have to count 4 times consecutive. The extrema equal to 0 crossing and equal to a given the same number. Okay. So this is basically our stoppage criteria. And these two give you 2 additional range. At the beginning, we're not so sure about the end effect. So a lot of time, we do not want to touch the endpoint. So this is the range. Is it beginning or end? So when you start to check these extremas, okay. But later we believe we have our endpoint effect pretty much fixed. So we can check from the first point until the last point, default. But you are free to set. You can only set the mid section, mid 1/3, or mid 1/2, or whatever, to check that so that it would be away from that. The bottom, there are two more bottoms. One is extrema shift, the other one is curvature shift. Okay. For the time being, we'll stay with extrema. This is easiest way. So if we decide to select this, accept this, we just click OK. It starts to run. Okay. It start to run through all the data. And as it runs, actually, if your eye is fast enough, you can see how many times it actually shifts to get that particular component. Here, we have actually get 9 components. Yeah. If you think this is acceptable, you say that the program end normally. You say Okay, then you will go back to the place that you want to pick up your data. Like, for example, I usually use MATLAB to load. I will load the data, and then I will load the SIFT result. Here is load the data, load the result. Then I will make a time scale. That's our time. Then we can plot. You can see this is our original data. This is the length of day data. There are 14,232 points. Okay, so here's from 1962 to 2002. Now we have also loaded the C62. That's the component. Anything important? Okay. All right. So we have already loaded the result. The result says 14,232 points times 9. We have 9 IMF components. So now I want to present the IMF components. There's one way that we can present it is to use the MATLAB canned program. This instruction is called the strips. That's MATLAB code. MATLAB code strips is C62. By the way, when you load the data in, load C62, this is our output. But for the program is written in such a way that when it come out, the column and the row it's transposed. So we have to, in order to plot it right, we have to say C62 equals C62 prime. We transpose it again. So now this is what we got. This is the data that goes through the SIFT. We get 9 components only. And these 9 components looks very good. You see this one is the half monthly. This is monthly, and then a couple months, and half yearly, and yearly, and more than a year, and then eventually to this. Then we even have a trend. And this kind of data is what I got when I first used this. I was very happy to find that the annual cycle stand out very clearly. Yeah. Now, if you change the programs, if you change the parameters in any way, let's go back. Let's go back and run this again. Let's say let's change this to 7. We still say okay. By 7, I mean I changed the stoppage criteria to 7. Okay. Now, if we run this, it will take a much longer time, and I get more components now. I get 10 components. Okay. If we load this in, what happened to Okay. I don't know why it sinks so low. It never happened to me this way. Anyway, now we have C627. This is 10 component. And we'll strip oops. I forgot to transpose, yes. This is annoying. I cannot see the line that I'm typing. Yeah. Here, I changed. The only thing I changed is the shifting time. What happened is that the half monthly is still up there, monthly is up there. Somehow, because I shifted more carefully, I counted more 10 times. You see the annual cycle disintegrated. The annual cycle, some annual cycle come up here, some annual cycle even up to here. Now I have severe mode mixing. Yeah, this mode no longer resides in this place alone, and some annual cycle appeared here too. So this is very nice annual cycle. The reason that this is nice is because our data is so bad. Our data has been averaged, smoothed, and there's no more noise. The noise already been removed through averaging. But as our data getting better and better, our results get relatively poor. Yeah, this is the way the program works. The program does not care what happened. What happened to your data? What kind of noise to the data in your data? The program just pick up the data and use it as it is. Now, let's say. Now we'll run this again. We'll load this again, and we say, okay. Instead of extrema, if you use curvature, see what happens. Okay. So we use curvature to sift, and if you collect curvature, and it again give me 10 components. But here the stoppage criteria is only it's only 3. So I forgot to change the output name, so I still load. This is better. This time, this is through curvature shifting. And curvature shifting, you see the large structure is still there and very nice. But you see, right over here, there are lots of hidden scales. The curvature we're able to identify, and it actually plot out all this. Let me plot this out in a little bit more detail. This is the first component that we got. And if you look at the first component, you see here it's pretty continuous. And on this side, it's totally disintegrated. Yeah. And if we look at any of the section in details, you see how nice the tidal cycle is? It's very regular. All right? But if we look at here, then we get all kinds of small, unwanted, small noise, small signature come in. This is no longer the tidal cycle. These are the short term, actually shorter than tidal cycle. Yeah, it get all sifted into this. And if we move to the other end, to this end, this appears all like non-tidal cycle, and these are our noise because we got such good data in 1996. Yeah. So when you use curvature, you have to be very, very careful. And to be careful, you see, in here, you will not see the kind of inflection point, wave with the inflection point, because the inflection point most likely was already straightened out by the curvature shifting. But it will give you lots more components. And of course, if you go down to for example, the tens, and that's actually the overall trend. And if for example, if I plot this together with you see, you see how nice the last curve is? The last curve right went through all the data. Yeah. So you don't have to look for trend, and that is the trend. And that trend is not obtained by running mean or by any other means. I don't know whether from the remote side, can you see the curve? Hello?
Yes, I can see. Yeah.
I can see that. It's a red line went through there. Maybe I should use a little bit different line, different color to make it a little bit. Let's see. Let's try that. Is that better? Probably not. Anyway.
Yeah, maybe here is better, I think.
It is?
Thank you.
Okay, thank you very much. So using curvature or using extrema, you pretty much get the same thing, except that the mode mixing, as you increase, you make your stoppage criteria more stringent. The mode mixing problem becomes more serious. Okay. So now having explained that, then we'll go to a different route. Here, now we only say that we click this, we put in the data, and we can run. We haven't checked that box yet. That box was invented or added in because we detect that we have severe mode mixing. And we want to get rid of the mode mixing problem. So we decide to have this intermittent test. And this intermittent test, if I click this, everything's still the same. Here I say, all right, will come out like I don't want to type too many. I will just call this C. Okay, the output will be C. So I say yes, and the data is ingested. I say yes, So now we still have a choice of maximum shifting time, stoppage criteria, the range that we check, and we select whether extrema or curvature. So we select extrema. All right. Now once we select extrema, then we say, okay, now here it's a different window appeared. This different window is that it says, if you choose -1, that means for this particular component, I will not set any criteria. If you choose -10, that means for the whole range, I don't want to check any criteria anymore. And so, for example, if we say -1, let's see what happens. If we say -1, we say, okay, this is the first component we got. And it will shift only one component and stop. And when you see this, you say, no, this is no good. I want to go back. You go back to where you start. And here you say, all right, I don't want any points that's not shorter than the half-monthly time. This half-monthly time, remember, this program counts the point between 0 crossings. So between 0 crossings is half wavelength. So if you set 8, then the full wavelength will be 16. That's already covered the half-monthly time. So here you say, for example, you say 4. If instead of -1, I say 4, then you go, so okay, so what happened is that we find a lot of small wave over there. Yeah, and you were successfully taking that out. Now, once if you accept this, you say okay, then it will make another choice for you, because the shifting is static. So by default, they already increased to 8. But if you decide not to accept 8, you still can change. You say, no, I don't want to use 8. I want to see whether there are some 4 still there. We still get some. In other words, this short wave, they are small crest, shorter wave, sit on top of the wave, sit on top of the wave. And once is not enough. And if you accept this, it will go back again to 8. You say you want to use 4 again. Now what you got is a flat line. That means there's no more wave shorter than 4 points between 0 crossing. Okay? At this time, you are pretty sure that you don't have this short wave anymore. Now, once you get this, then you can go back. Because this is useless, you go back. Instead of that, you say change to -1. So now I don't have anything anymore. So now I want to take the next wave. If you say this, then you say okay, it will give you this. This is a half-monthly time without a lot of fallout. So this is a very clean half-monthly time. By clean, I mean the scale should be all half-month. But obviously you can see the amplitude. The amplitude is still not very clean, because here we do have a lot of data in recent time. We have all kinds of GPS satellite to give us the wobbling of the Earth. Over here, it's so smooth. Not because the global warming gives us an erratic rotating speed of the Earth. It's not so. It's just because our data is too good. Yeah, our data is so good that we will see the detailed changes. And if you look into the reasons that will cause Earth's rotating change, you will find all kinds of that. So one of the reasons that discovered by Ben Chao, the dean of our Earth Science School, College of Earth Science, and he found that even if you build dams on land, build a big dam like the dam in along Yangtze River. You suddenly stop the river flow. You store lots of fresh water in there. Then you change the distribution of the mass around the Earth. Okay, that is enough to cause the rotating speed of the Earth to change very, very little, perhaps less than tenth of a millisecond, but nevertheless there will be changes. Okay, so in this case we get this very nice half-monthly component, and if we say okay, they will go back here to say you still want to use -1, and if you say okay, then this will give you a half-monthly time. Okay, and in this way, if you check intermittency, you can actually see each component as it appears. And if you do not want to interfere, you just keep on using -1. You can see click, get one component, click, get another component, click, get another component. Yeah, so you can keep going to get this component. And on top of this, there are a row of bottoms. This bottom you cannot change, but this bottom you do. Some of the bottom you here they give you maximum semi-wave, that's 34. Minimum still 3. This kind of small. Here is shifting only 5 times to get this. 一下一点 ，OK. Oh, I'm sorry. OK, 摆在当中。OK. So here is OK. You accept this. This is go back. That means you go back to where you start. And the third bottom here is called option. If you click that option, it will come back to here, which you want to change a parameter. You say, all right, if I check the change parameter, you can actually come back to here to change parameter. In other words, when you're shifting, you decide to say, gee, I get tired of using extrema. You can come back here to change the curvature. And you say, I don't want to use cubic, and you can use other spline. So you want to change stoppage criteria, you can change every other thing at the initial. The only thing you cannot change is to stop the intermittency test. Okay. So this is actually the shifting machine we use when we're doing some development. Okay. Again, don't try to use the other 4. You use 4, you may not converge. Use 1 or 2, it's bad. I believe one of this is linear. Yeah. So this is basically the thing. And if we do not want to make any change, we click OK. Then we get back to here. And we can keep on going. Says OK. And if we accept that, we say OK. Aha, over here, you will see that's very poor, very bad mode mixing. And if we think this is not acceptable, we go back. We say go back. I cannot use -1. Now the next major component will come out is actually the half yearly. So half yearly is 180 days. Okay. So if I use 45, whoops. 45, that gives us 90 days, which is still away from half yearly. If you say OK, then we get a few out. That's no good. We go back. We insist on do 45. No more. We go back. And then here we say -1. Let's see what happened. OK. Yeah. See, we get half monthly. Using this, you can see component after component. And then each component, you will be able to judge. And if you accept this, you say, OK. Then you keep on going. This is the annual cycle. How do I know it's an annual cycle? Because I have done this data so many times. Now here's the, you can tell this is the annual cycle. That's 1978 amplitude and so on and so forth. Now at this stage, you say I don't want to do any more. Then you put a 10 minus 10 is okay. Then we just go through it. Now, how many components we got? We get 12 components. If you load if we load this in and this is what we got. See, we got the first two looks almost the first two just a little bit of blip, little bit noise, and this little bit of blip are coming from the very detailed data that give us detailed rotating speed of the Earth. Then we get this half monthly, monthly, and we also get this very nice annual cycle. I probably somehow I did it wrong. I probably did not go back enough to catch this. We should go back to check. Somehow I made a mistake. And this we're able to influence the end. And otherwise, this annual cycle come out very nicely. Yeah. So you're able to play with this program. And this program, however, has one interesting thing. That is, you see this, the original, at the beginning we get the two hump, one longer, one shorter. But once you use intermittency, the longer and shorter will get separated. Okay? Separate in two. So this is the way that we got the result. Now once we get the result, there are a couple of things we want to make sure whether this result is good or bad. One thing that I like to check very much is to see, are these components actually orthogonal to each other, or how about the orthogonality? In the program, I think we have given you, I don't know whether we did or not, but there's a this is a program called the ratio A. Ratio A, you put ratio A C, and you enter, it will give you a string of numbers. Okay, this string of numbers actually check intermittency. This is the component number 1 to number 2, and number 2 to number 3, number 3 to 4, 4 to 5, 5 to 6, 6 to 7. You see that all the orthogonality index, it's no more than 1%, no more than 4%. Most of that is actually 1% or something. So this decomposition is actually pretty good from the orthogonality point of view. Yeah, this is pairwise. Now, if you want to check the total, that means of all the Ci times Cj, if I does not equal to j, yeah, then you get minus 0096. It's around 1%. So the total non-orthogonal total projection, it's very, very small. Yeah. So this actually is a pretty good thing. Not only that, when we get this, even though these first two components looks separate, but both of these are noise, and their noise may be separate scale, may not be separate scale. Remember, we use the same length criteria to fetch these two out. So if we plot this out, So if I plot this out, I will have both C1 and C2 plotted on the same scale together. We see that here is a C1 and C2, and over here we have a few points. And if I blow this up, you find that this C1 and C2 are actually not exactly the same location. Yeah. So what we can do is to combine the first two as just one component's noise anyway. So just lump it together. There's no obviously separation in scale. This is also small and this is small. And it does not happen at the same time, so same place. So they are orthogonal to each other, pretty much orthogonal to each other. Okay? So this is how once you get this, you can plot this in different way. The other way, once we get this data, the other way to use this data is to construct a Hilbert spectrum. Even though we haven't got there, but I want to show it to you how to compute. We have this let me do this. Okay, help. Okay, this is the program that actually compute the NNSPE means the spectrum compute energy as energy spectrum. And this energy spectrum, the input here, there are many inputs. The input you want to put your data, the data actually is your IMF components, the output from EMD. Then you want to tell them the beginning and the end time. This beginning and end time, you want to tell them the true time. For example, if you say that, okay, my time is 1962 to 2001, you just type 1962 to 2001, the physical true time. Once you put in this true time, then the frequency is to be computed based on this time. Okay, the cycle per this unit. If you put in an annual, that will come out cycle per year. And if you put in days, it will be cycle per days. So the answer come out. This becomes, once you put this as a true starting and end time, that's a physical time. And that physical time will be used as a base to compute the frequency, the instantaneous frequency. Then the frequency resolution, because we have different using EMD, we can, even for the same data, sometimes we get a different number of IMFs. All right. So if we calculate the instantaneous frequency as a continuous curve, then we'll have different number of curves. It's very difficult to make comparison. So, and also at the beginning, we are kind of limited with our computer power. As I said at the beginning, when we developed this, the computer I used was 286. Perhaps you have never seen a 286 in your work. The 286 is a very, very slow machine. Yeah. And at that time, it would be almost impossible for us to do this 14,000 data points. 1,000, 2,000 points is already a lot for us. So So we, at the very beginning, we decide to project all the data into bins, horizontal bin, vertical bins. So the bin, we have to put the resolution. So how many frequency, what's the frequency resolution? How many bins you want to put in frequency? You can select 200, 100, and 300. Now we have computer, even laptop, I can choose 1000 without too much problem. And the time resolution, so we got 14,000. You really need every point, or how about say every other point, or 10 time step a bin. So this gives you the true frequency and time resolution that you can select, and this is very, very different from Fourier. We're going to come back to this when we talk to the spectrum, but since we are here, I will just explain to you, so I don't have to log my computer into at that time. So this gives you the frequency resolution, time resolution, and also here it's another feature that we build in. That once you made a computation, you don't have to see the whole thing. You can actually zero in like a zoom. You say, what frequency range you want to see? Instead of see the whole range, you say, I only want to see, I put all the resolution in very narrow range. This narrow range is 0.1 hertz to 0.2 hertz. And you have many, many points. You have this, say, if you select a frequency resolution to be 500, if you put 0.1, 0.2, then in 0.1, 0.2, you have 500 steps. Yeah. And you will still get different values because we take a derivative, and that derivative has a lot of resolution. The resolution is actually not limited by your digitization rate, but by your precision of your data. And you take a derivative of that, you can get any value in between. So the frequency, time resolution, frequency range, and time range, maximum time zoom in and minimum time to zoom in. Yeah, you can zero in at just a very narrow time span. So I want to examine what happened in this particular location. This gives you a choice. Then the last few, it's a little bit different. That's IMF method. What method you want to use to compute the instantaneous frequency? Okay. Here we have Hilbert. We have HILBT, abbreviated Hilbert. Turns out that the abbreviated Hilbert is more sophisticated than Hilbert. The Hilbert transformation they give us in the MATLAB has a severe problem of N effect. Yeah. When we talk to Hilbert transformation, we'll talk about N effect of Hilbert. Why Hilbert has N effect? Because Hilbert was implemented with two Fourier transformations. Yeah. If the beginning point and end point is not the same, the answer is going to look very bad, very poor. So we fix that. We also use arc cosine. We use zero crossing. We use quadrature. We have all different kind of way to compute instantaneous frequencies. Yeah, and we're going to talk about that when we get to the instantaneous frequency. And then, in addition to compute this instantaneous frequency, in the process of computing instantaneous frequency, especially when we're using arc cosine, quadrature, Hilbert, even if it's IMF, that's only necessary, not sufficient. It still may not be good because they are mathematically there are two more theorems limiting the performance of Hilbert transformation as a tool to compute instantaneous frequency, to compute the phase. Okay, so in order to do that, we have to normalize our data. this normalization is a way that to separate the data into AM and FM. In the frequency computation that we are dealing here, we are strictly dealing with FM. We should take the amplitude away. In other words, the whole function becomes unit amplitude becomes a cosine theta, and we want to find out the theta. If you put A in, that causes extra complication, because the A is AM, and when you do Hilbert transformation, then that will have both AM and FM. So you have, has option. It either say, I don't want to normalize it. I want to use Hilbert to normalize it. I want to use a spline to normalize it. I want to use a linear line to normalize it. And you want to use Hermite cubic spline to normalize it. Yeah. So after this, we have one more thing to worry about. That is the last thing that we put it here. The last thing to put it here is the number of filter. The frequency we compute is by differentiation. So everybody knows differentiation generates noise. And if you really want to look for trouble, take your data, take a derivative of the data. Of course, all the little things becomes amplified. Now, in here, we know that if we take a derivative, we may have problem. And a lot of time, that a short blip can get blow up, becomes very large. So here we institute a filter. The filter is a medium filter. You can take, for example, if you enter medium filter 3, then you will have every 3 points. I will only take the medium points. The outlier will be kicked out. Yeah. So that way, we will compute the Hilbert spectrum. And this is the detailed explanation of using Hilbert cosine, Hilbert TMs, using Hilbert transformation, but it's used instead of standard Hilbert transformation spline. And so now let's just try on this particular. The output. The output is given here. The output is a matrix, which is your final matrix of the given resolution, time and frequency, and time scale and frequency scale. And then once you put it in that, you will be able to do. Put N as our matrix, T is our time scale, F is our frequency scale, and the input here, because we have the input here we have is C. So the input is C. And the next come in the beginning and end time, beginning 1962. And the end time is 2002. 201, and year of 201, yeah, 202 I should say, 202. And after that, frequency resolution, let's put 200, say. And time resolution, let's put 1400. So it's 14,000 would reduce to every 10 times, okay? And after that, we want to say frequency range. Frequency range, we want to see from 0 all the way to, say, like 40. Actually, 30 would be enough. 30 cycle per year, yeah. Take 40, okay. Then time scale is from 19 62 to 2002. And that's all the number I want to put it in. Then normalization, for example, normalization, if I use Hilbert method to normalize, and use Hilbert to calculate that, and I use a three-term, three-point medium to filter it. Whoops. I forgot to put a point in between. Yeah, okay. Whoops. Oh, sorry. I cannot see very clear here. 都错。Let's see. 202, 200. This may be right now. Whoops. Let's see. T1, T2, frequency resolution, time resolution, and okay, F1, it's 0. Should be 0, 40, 1962 to 202. This time should be good. Whoop. Must be positive integer. I don't know why it doesn't work for me. I should practice at home. See whether that will make any difference. 还是不行啊。嗯。I don't use Hilbert. Let's use spline. See whether that makes any difference or not. Okay. Now we have it. Then we can use the What is this? I don't know why it doesn't work. I'm sorry. It should work. How many components we have? C is 12, okay. 1 to 10. So does that make any difference? Okay, still doesn't work. Huh. I know why it doesn't work. Because in here, in our component, we have this big, huge hump. I put a huge hump in. So the magnitude is so small, the magnitude only appear in the last component. So in desperation, I changed it to log. At the beginning, I was plotting TFN. I plot TFN, nothing happened. I raised it to a higher power, nothing happened. Okay, that means the magnitude of separation is so big. So no matter what I've done, it's not happened. I took the last component out, it's still not working. So finally, I put a log absolute of n. So when you take log, you want to take only absolute value. So you take log absolute n, you get this. We finally get it right. And here we have this half monthly, monthly tie, and half annual, annual cycle, and so on. So we get all the number right. And when I presented number, sometimes it's really really hard to see, and also it's very jagged and the line are very thin. So I usually put a filter in. I usually design a Laplacian filter, and if you this is the kind of Laplacian filter I present. At the center point, it's the maximum, and it gradually comes down. And using this Laplace filter, you'll make the figure looks much prettier. And what you do is n equals to and you can do it a couple of times. Sorry. After it went through this, you see this becomes much heavier. And in this case, maybe we can take away all this away. Let me see whether that will work. Or still doesn't work. So we still need log to get. We have included, see, we have included such a strong number here. So this is typically the way that I analyze it, and then we can also do marginal spectrum. This is the marginal spectrum. I have already smoothed it too much. See, this is the half monthly. This is the monthly. Yeah. Anyway, so this is the sequence of the thing that from the beginning of the data all the way to spectrum and Hilbert spectrum and the marginal spectrum and so on and so forth. Yeah. The program, I don't know. Have we put all the programs on the website for people to use? 我们有没有把 program 摆在 website 上面? If not, you should go to the program should be available at the NCU, National Central University Center for Adaptive Data Analysis. Yeah, we should have a few, and if not, we're going to put in more. Okay, go back and check the NCU site. If not, we're going to add more. So this is basically how we operate. We operate the sifting machine, and once you get the answer, how you manipulate it. So, is there any question about this? How to work on this sifting machine on this particular one? Especially this one is different from the other ones because this one has intermittency and this one has curvature. But once we covered ensemble, you will find that the ensemble actually is more interesting than the straightforward EMD, the ensemble EMD, EEMD. But there's no free lunch. EEMD has its problem. When we come to that, we'll discuss the problem of EEMD. So, any more problem? Questions? So you should be able to manipulate this. We still have 15 minutes. I'll give you a little bit introduction to Ensemble EMD. I don't know what happened to my computer. It's become so slow. So maybe a little bit shy. Okay. Ensemble empirical mode decomposition. It is also known as noise-assisted signal analysis. Okay. This is very different from the one that I posted. Please download this instead of the one that you have. Anyway, the changes. And this method is developed very recently. It was developed in maybe 3 years ago, and it was never published because we want to patent it. Okay, and now the patent's done, and it appears now in the new journal called Advances in Adaptive Data Analysis, Volume 1, Page 1, page 1 to 14. Listen, we're living in the future. This is not now. I get advanced copies. So it should be inaugural to come out in 2009, but I get advanced copy. This paper, you should be able to download. And I think we have that paper posted on the web. So you can download the paper, read the paper first. And if you read the paper, you'll get everything that I will cover. And what this is ensemble empirical mode decomposition, noise-assisted signal analysis. We use noise to help us analyze data. And this is a pun. If NASA, it becomes NASA. I work for NASA. So we try to poke a joke at the NASA people. It says, listen, what we're working on is NASA business. Yeah, it's noise-assisted data analysis. This whole method is dictated by the following requirement. See, I have shown you, if we use intermittency test, we can actually separate different scale very nicely. Yeah. Then why do we need another thing? Yeah. The reason is that if we use intermittency, you can see that how I went through. When I use intermittency, I have to put in a criteria. The criteria is the wavelength. Okay. And in order to put the wavelength, you have to know what kind of wave you want. Yeah. So in this particular problem, like the length of day, it's simple. I can put in the month. I know there's monthly, half yearly, yearly. So half monthly is 15 days, 14 days. Half yearly is 180 days, and yearly is 365 days. I know those scales, then I would be able to do it. Yeah. But what if I get into a situation like a turbulence measurements? They are fast-moving fluid and slow-moving, and they're mixing together. I don't know the scale. And not only that, the scale may not be so discrete, like half yearly, yearly, half month, a month. It may also mix, and a change may be continuous. So there's absolutely no way for me to invoke the a priori criteria. And the worst is the philosophic problem, is that if I know, even if you know the right number, but that right number is your subjective choice, so it destroys the adaptive nature of EMD. So at the beginning we say EMD is adaptive, Now it's no more adaptive because you put it in a number there. You tell the shifting how to behave. So the intermittency test is good, but it's no more adaptive. Not totally adaptive. Okay, the scale has been preset by your criteria. Nevertheless, we will see later that there is a need for us to still use intermittency. We'll see later. Then we use EMD to study white noise. And it turns out by studying white noise, the white noise behaves so well, it generates a frame of scale, a natural frame of scale for us. White noise is the noise that has all kinds of scale. Now, once we use white noise, we find that this white noise help us to establish the frame. It sort of like put a great work for us to define frequency, and that's very nice. Now, once in data analysis, the thing that we dread the most is noise. Now, if we introduce white noise, what will happen? We have to suffer the consequence of introducing noise. So the white noise has another very nice property, is the cancellation. If you add 1, it's noisy. Add 2, it's noisy. If you add infinite many, the white noise cancel each other, then it will come out as if there's no white noise. So we use all these possible properties to decide that we'll use noise actually to help us to sort out the scale in a nature way. So background number 1, it's intermittency. We don't have to look at this. We can skip all the intermittency part. The reason I put this in is that this has been a standalone talk by itself. We will skip to study white noise. This white noise, again, is a paper that we published in 2004 in the Proceedings of Royal Society. I believe you can download this paper from Royal Society. Royal Society has a very nice policies. Any paper they published beyond 2 years, it will be in public domain. Anybody can download it. You don't have to have a subscription to that. And if you have any problem, download this, let me know. I have a copy, I can put it on the web. And maybe we can put there for the class. This is based on the observation, a Monte Carlo experiment with 1 million points. We generated 1 million white points. And that 1 million white points, we cut it. We get IMF by 10 shiftings. Instead of changing the stoppage criteria. The stoppage criteria we use here is strictly 10 shifting. Each component generated by 10 shifting, 10 steps. And for the Fourier spectrum, we use 200 Fourier spectrum, and each one consists of 4,000 data points. And for the probability, we use 50,000 data points to generate this. I want to go at least to this view graph before I end this class. When we put the white noise in the EMD, something very nice happened. That is, for the million data points, we got 9 components. Okay, the 9 components has very interesting properties. That is, if we count the extrema, we have 347,042 extremas. Yeah, 300,000 extrema. But don't look at this number. Look at this number. This number is that mean period for each wave on average is 2.88. certain wave longer and the other wave shorter. This is white noise. Okay, so the average wavelength is 2.88, not quite 3 points for the white noise. That's the first component. You look at the second component, it's 5.946. 5.94, it's almost 6. This is almost 3. So this is almost twice of that. 5.9, and then the third component is 11.98. This is very close to exact twice of that. See, 11.8 is almost 12, and this is almost 6. So that's 12 to 6. And then the fourth component is 24. 24, this is 12. This is almost twice. And 24, 48. This is 47.9. 48, 96. 96, 190, 192. This is 189, and so on. So what this means is that the EMD is a dielectric filter. By dielectric, it's an increase from this by 2, by 2, by 2, by 2, by 2, by 2. Yeah. At the very beginning, we detect this. And that's why in the intermittency test, the length scale, we double each time. Yeah. And we use white noise, we actually get that. We actually get this double, double, double. Yeah. And because we use so many data points, 1 million data points, we believe this is right. Now this property is observed by us. At the same time, it was also observed by Patrick Flandre. Yeah. And Patrick also studied white noise. And Patrick actually studied more different kind of noise. Not only white, but also studied colored noise, like red noise and brown noise and different kind of noise. White noise has spectrum is flat, and red noise spectrum is -1 slope. So Patrick Flandre was able to study the noise and tell you what's the color of the noise. Yeah, and I will give you that reference too. But all of this is a very interesting result to us, and it's amazing. So by studying this, we repeatedly confirm that this EMD is a dielectric filter. And not only this, the more amazing thing is that if you draw the spectrum of each component, what you find is that the spectrum of the components all look like this. They are similar to each other. And except this one is a little bit off. But this similarity, when you plot on log, is so well that you can collapse all the spectrum into one shape. So you can unify it. You can normalize it. Yeah. And so this is what we got from white noise. And this is a extremely interesting property that we got. So do we have the white noise paper on the website for the class? Mail. Okay. But this white noise paper is at NCU, Research Center for Adaptive Data Analysis. So go there and download this paper if you want. You can read it. And also try to read that Ensemble EMD paper, which we have already put it on the web. Yeah. So we'll stop here. You think about this interesting properties, how we can use it. Okay, we'll start from resume next time. Next time we'll start from here. All right. Thank you very much. I'm sorry that I stumbling around on the computation. I'm very poor at the typing and very poor at the computation. Yeah, in programming. All right. Thank you very much. Yeah.
Thank you.
Sure. By the way, we have class here next Friday, but the following Monday we don't have class. Okay, and then the following Wednesday we don't have class. The following Friday we have a different for people here. We have a different meeting place. I was told that we have to change meeting place. Do you know that? Yeah, 他们讲换教室. We will find out that. Anyway, see you Friday. Bye bye.
See you. Bye bye.
You don't have to go. Do you have any questions? Yes.
你用 white noise 啊 ，white noise 是那个 energy 都一样，在不同的频段。
是。
那所以我们等于可以找到那个频率的变化的那个 frame。那如果是我一个 energy 的变化的
frame。Energy doesn't matter. Energy, see, the decomposition does not consider energy. The decomposition only considers scales. So your energy can still change from place to place. But the first step that we do is to decompose by linear time, by the temporal scale. The energy will come out at the normalization step when we compute the spectrum. Yeah. 这个问题，你们大家听懂他问题没有？他说你这 white noise 是 energy uniform， 拿着 white noise， 我们的数据假如不是 uniform energy 的话怎么办？那这个我们的 decomposition 是主要是分 scale， 不是分 energy。energy doesn't come in， 呀、yeah. 要紧的是分这个 energy。At the end of last class， 有一个人问我一个问题，他 promise 他 repeat the question at this class 。OK
现在就是不同需求的不同三 criteria 会不同的三 criteria， 除了对任何一个 model 来说，不同三 criteria， 现在是应该我再从头来。
好，从头来。
就是因为前面有一段陈述，后面才能够讲，就是现在是用上一节课是用密来度量说你是不是那个有 anomaly 在？应该说你用很多个不同的三 criteria 得到不同的结果，
是。
不同的结果，那你现在把不同的结果取它的密当做一个 reference， 然后不同的结果去看离这个密有多远。如果说每一个离得很远，比如说 standard 已经很大的时候，是代表说这上面有anomaly在。那结果也是这样看，就是因为从结果上看到这个样子。那是不是有可能说反过来说，我是不是可以去 detect 哪里有哪里有？
不是这个 anomaly， 我们上次讲那个 confidence limit 啊，它除了 anomaly 之外呢，它那个 anomaly 不是真正 data 里的 anomaly， 它的 anomaly 是 deviate from the mean。OK， 我们 create 一个 ensemble， 这个 ensemble 呢，因为我们把它拿去这个 decompose， 我们怎么知道哪个 decompose 好，哪个 decompose 不好 ？Especially 我们有 different stoppage criteria， 一个 generous， 一个 generous， 这个 generous 5-6个，我知道哪一个对呢？但是我想就是说这个 true answer 啊，大概是在这个 neighborhood。OK， 在这个 neighborhood 哪一个是最接近于这个中心呢？我们就采取了民主方式，就是投票啊，投票多的这个就对啊。We adopt the democratic way. We by vote. Whoever get the most vote is counted as the right answer. So that is the way that we use. That's not a way to detect anomaly in the data. It's to detect anomaly from the ensemble. 啊，是不一样的，就是这个 anomaly 是 from the ensemble we create. The ensemble is created by different stoppage criteria. 每一个 criteria 都应该有一些 information， 但是哪一个 information 最多呢？我们就认为就是说那个最 stable 的那个地方最多。什么地方最 stable 呢？就是你变了一遍，它变得不多，呀，变得不多的地方就 可能是对的，呀，这个也是一个 assumption， 呀 ，but it turns out 啊，就是你用这个东西，用这个 criteria 做出来的 result 是比较合理，啊。
那现在另外一个讲法就是那个subject 还有越紧的话，mode越多。
是。是。
然后换句话说就是，如果说你用 Fourier 的观点来看，
是。
真的就是 bandwidth 越
呀，但是Fourier 你这个我们等一下我们会在以后我们会讲啊，就是说我假如把这个 stoppage criteria 定得非常紧呀，那我这个 mode 非常多 ，what is the limit？ 这个的 limit 是很我们现在是一个 conjecture， 我们没有办法 prove 啊。这个 limit 呢，到最后就是说我们也可以 generate infinite many， 不是 infinite many 了，就是 generate many mode。这个每个 mode 跟 mode 之间它的 frequency 的 difference 不是2:1，而是1:1 almost 1:1，像 Fourier 一样，呀。但是我们永远不会到 Fourier， 因为什么呢？因为我们到最后那个它的 length scale 还是不是 uniform。Fourier 连 length scale 都 uniform， 呀。
那 Fourier 虽然它是看整段的资料，
对。
但是这个是任何一个点都可以看。
对。
那任何一个点看，当然就是那个就是不一样的事情。
是。
任何一点可以看那个可以体现事情发生在哪里。
是。
然后在这一段。
对，所以它就是变了那个样子，它跟 Fourier 还是不一样。我们到最后可以变成 FM，Fourier 就是根本就是 constant frequency， 我们那个 frequency 还有 oscillation， 就是 amplitude 没有 oscillation。我们在讲的时候会讲那个，呀。OK， 还有没有问题？好，没有问题，我class dismiss， Thank you。